with you. Without further ado, please, Gabriel.
Okay, thank you very much. This is very exciting workshop. I'm very happy to be here. I'm kind of an outsider. My original training is completely different in cancer research with magnetic nanoparticles, and I slowly, it's almost like a Brownian motion, kind of diffused to where I am today. And I'm really happy to be here because I am a huge fan of AMO in general. I think AMO is, for me, the field that is really in the kind of multiple frontier between different fields. You know, AMO people, they understand solid state physics, they understand field theory, they understand quantum information, and I think this is really nice. I like this idea of being able to talk, you know, across fields. So I'll try to show you a little bit of what we've been doing over in my group at the University of Rochester in the last couple of years. So I will start by taking the following paradigm that, you know, no one sees quantum systems. No one ever saw a quantum system, right? Well, they see data. We just get a bunch of data, and we have to now infer from this data what is going on. What is the underlying quantum system? Now, for me, I always like to think about the process of measuring a quantum system physically by bringing in some apparatus, some ancilla, and making the ancilla interact with the systems, right? So that there's some interaction step, and then you measure the ancilla and you get some data point out, right? I prefer to think about it in this way because it naturally accounts for this information back action trade-off. If you want to get more information about your system, you have to increase the interaction strength, which means that the back action is also going to be higher. Now, the usual way that we think about quantum measurements is in this prepare and measure scenario where essentially you bring in an ancilla, you make it interact with the system, you get a data, and then you reset, right? You completely restart everything, and then you do everything fresh. The system is freshly prepared, the ancilla is fresh, and then you repeat. And what you get out of this is data that is IID, independent and identically distributed. Right? This is the usual textbook way of thinking about quantum measurements. So what I'm interested here is an alternative way of doing measurements, which is essentially sequential measurements. Essentially, now I don't reset my system in between steps. After I get one data point, I bring in a fresh new ancilla, fresh new apparatus, I measure it again, but the system is still the same. And what this means is that now the outcomes are going to be correlated. Right, so each data point that I get from each measurement is no longer independent of the previous one. Of course, there are plenty of examples of this that you might be familiar: quantum jumps, you know, quantum diffusion, and so on. We'll go through some of these examples, but this is kind of the paradigm that I want you to have in mind. And this is a simple textbook example, perhaps the simplest one that I can think of. Suppose you have some qubit and you want to measure it projectively in the computational basis, and also apply unitary. So what you do is you do the following game, you prepare an initial state psi 0, and then you apply a unitary and you measure, right? And this is Born's rule, gives you the probability that you're going to obtain the first outcome x1. And if the outcome that you obtained was x1, then you have to update your state to x1. Now, for the second step, you get now a conditional probability distribution. You get, you know, x2 given x1, because that's exactly the whole sequential business, right? This probability is now you start at x1, you evolve, and then you measure again. And so this is depends on the previous outcome, and then you also update your state to x2. Now, what you get out of this is a bit string of symbols, right? Your measurement outcomes at each step, and the probability that you observe a certain sequence now forms a Markov chain, right? Because essentially, since the projective measurement is so strong, every time you measure, you completely destroy previous data. And so each xn only depends on the xn minus 1, right? But now already you get something that are not IID outcomes, you get correlated data. Okay. Yeah.
How different is this approach from, for example, in quantum error correction, where you need to do, for example, intermediate measurements or mid-circuit measurements?
Not different at all. Not different at all. It's still the same sequential measurement. Well, all that changes is what kind of measurement you do. If your system is multipartite, then you only measure one part of it, and so on. So I'll slowly build up to a more kind of general framework. This is maybe a little bit too idealized. I'll build up to a more general framework where essentially, yeah, any kind of sequential measurement that you don't reset, it's absolutely fine. Okay, so if you want to be a little bit more general, one possibility would be, you know, doing generalized quantum measurements, which are described by a set of Krauss operators, F, right? And in this case, the recipe is exactly the same. You have some probability of outcomes at each step, and then you also update your state, but now the state is not a ketchup size, some density matrix, and you have to apply F, density matrix F dagger, for each outcome that you obtain, and you just kind of repeat it in this way. So these are the basic recipes. This tells you how to generate the next outcome of your measurement given all the previous data. And so essentially this depends on the measurement that you're applying, your F, and also depends on the density matrix from the past. And this tells you how to update the state given what you obtain. Now, what you get out of this, if you apply a generic kind of generalized measurement in this sense, you get a data set that is now highly normative, right? So you could have very, very long history memory in your data. So this is important to realize that the evolution of the system is Markovian, but the evolution of the data is not, okay? So the system is evolving Markovianly because at each step, the system just, the step that it goes just depends on the previous one. But the data that you get out of this could have very, very long memory. So this is akin to a hidden Markov model, where the system is now what's called the hidden layer, is the thing that you don't see. All you see is the emitted symbols, the data, right? And so this data could have very, very strong memory, even though the system is just evolving Markovianly. Okay, and I want to do one final kind of generalization, which I have learned that it proves really helpful, you know, just in terms of thinking about problems, which is that instead of thinking about Krauss operators as things that act on density matrices, maybe on the left, maybe on the right, you can just think about just a super operator, which is generally called the quantum instrument, which is just some super operator acting on density matrices, right? This cleans up the formulas quite a bit. It's kind of nice because you just have, you know, everything becomes more compact, but it also greatly generalizes the whole thing because you can consider now a much broader class of measurements. In fact, in terms of these instrument objects, you can actually encompass any kind of sequential measurement. For example, you can consider what's called inefficient measurements, right? So measurements which are like bundling of outcomes. Suppose, you know, your emitted symbols are like 1, 2, 3, 4, but you can not distinguish 1 and 2, right? So you want to bundle them, and you can do this very easily with instruments and so on. And so now what you have is a set of instruments, and diagrammatically, you know, the instrument is this entire thing here. It encompasses the ancilla, the type of interaction, the type of measurement that you do in the ancilla, and so on. It's just this object that tells you how the system is processed and how the data is produced. And this is essentially the basic recipe, sequentially, for how you generate each data point. And this is the, if you want to do the probability of an entire string, right? So this is kind of very convenient language. The other thing that you can also do, which is nice, is to consider what's called the unconditional dynamics, which is whenever you measure, but you don't really read the data, right? Because so this essentially you average over all possibilities of the measurement, and so what this gives you is that each step is now a proper quantum channel, like CPTP quantum operation. In the language of master equations, some people call this a collision model. You can imagine that, you know, each interaction here is a small kind of particle that is coming from the environment colliding with the system and flying away, right? And you can build master equations using this kind of idea. So this is the unconditional dynamics. It's the dynamics when you're ignorant about what actually happened, about what actually, you know, you don't know what measurement outcome you got from the ancilla, right? The ancilla is still interacting. There's still a back action in the system, but you don't know what's going on. Okay, now the first thing that I wanted to point out is really this connection with hidden Markov models that I find quite fascinating. So a hidden Markov model, it's especially cut off here, sorry for that, but a hidden Markov model is defined on a sequence, a discrete set of states, right? So for example, A, B, C. And you can completely specify a hidden Markov model if you give this probability, which is the probability that the system goes from a state sigma prime to another state sigma, and at the same time, it emits a symbol X, right? So to each transition, it emits a symbol, right? And so if you know the probability that it goes from here to here and also emits a certain symbol, that's completely defines the hidden Markov model. And now, once you have this kind of probability, you can make predictions, for example, about what's the probability that a certain symbol is going to be emitted. So this would be suppose you have some kind of prior probability here for your hidden layer, and now you just use this transition probability to generate the, a guess for what the next symbol is going to be. In addition, if you observe a certain symbol X, you can do a Bayesian update. You can update your knowledge about this hidden layer here by just looking at the posterior. Now, I can rewrite these two formulas in a slightly more suggestive way. If I define, I have this kind of 3-index object here, X, sigma, sigma prime. And for each X, I define a matrix with entry sigma, sigma prime. And I also define a vector, which is like a trace. It's just a vector with a bunch of ones. And then I can write the update formula, the probabilities and the update formulas in this kind of convenient way. And this, I want to compare, with the formulas that we get for instruments. And you can see the similarity. So essentially, we can describe the dynamics of sequentially measured systems in a way that is very, very similar to the dynamics of a hidden Markov. But there are fundamental differences, right? Because a hidden Markov model lives in a state space, whereas sequentially measured quantum systems live in Hilbert space, right? So for example, instruments could have complex entries. In a Markov process, these stochastic matrices, and there's nothing complex in them, right? It's just like random probability stuff. So here there could be interference effects and so on. So it is a stochastic process in Hilbert space, but there is a close analogy to hidden Markov models. Now, one reason why this is useful is this idea of prediction, right? So remember that I said that the data that you observe have very long memory. In principle, the probability that you observe a certain symbol being emitted could depend on the entire history, and that could be very complicated. But if you happen to know the density matrix that the system is in, that's all you need to predict the next symbol, right? So this is a data compression. Instead of knowing this entire sequence of data points, you just need to know where the hidden layer is in, what density matrix it's in. Right, so if you know the internal state, you can actually make predictions about future outcomes. And there's various kind of interesting things that one can do with this. For example, in the kind of more classical sense, people are using this to predict essentially outcomes in large language models, right? So suppose you use ChatGPT and it spits out some text, right? That's the emitted symbols. And now you want to say, okay, how do I infer the internal state of the GPT from the emitted symbols? And if I know the internal state, I can predict what symbol is going to be emitted next, right? Probabilistically speaking. So there are people that are doing a lot of this kind of related stuff using these predictors. And you can also do, this is a very nice paper that I recommend on essentially focusing on these ideas of predictor models. I'm not going to talk much about this. Yeah?
Sorry, I think I got lost somewhere on the way. So all of this makes sense if you assume you know certain things about your system. For example, what the evolution from some xn to xn plus 1 actually means internally, right? Because otherwise your first line of your first statement is not true.
So you're saying you need to kind of know the model?
Yes.
Yes, that is true. That is absolutely true. You need to know essentially the instrument.
So your whole kind of chain model makes sense if you basically know already the modular steps in it.
You know that, if a certain symbol was emitted, what kind of action that's caused.
Yeah.
So for example, you know that if you have an atom and a photon was emitted, you know that it means the atom must have decayed.
Okay, yeah.
That you do need to know.
Yeah. Okay, thank you.
Okay, so now I want to specialize this to quantum jumps. So I want to advertise a little bit of a tutorial that we have put out in this paper with some folks in Dublin and in Basel, where we essentially discuss very nice connections between these ideas of sequential measurements and things that some people use in condensed matter and also other techniques that people use in quantum optics. And we try to kind of connect some of these tools. So you can find the reference here. And so for quantum jumps, essentially what you have is some kind of Lindblad master equation, which has a set of jump operators Lx. And in this case, if you want to define some instruments, you can define a jump instrument, which is essentially apply L rho L dagger. And so you have a number of jump instruments, each one associated to a possible jump. And then you also have a no jump instrument, which applies a kind of no jump evolution, right? So now at each time step, your evolution is given by either you jump or you don't jump, but jumping is very rare, right? So most of the time it is evolving smoothly, and every once in a while, boom, there is a jump, okay? These are just some examples of how these kind of continuous quantum jumps can be implemented in some papers that I like. So this is essentially the quantum jumps are individual photo detections. I mean, the whole idea of quantum jumps originally is from quantum optics, right? And so this is a kind of exactly what that means. So a quantum jump is just a click, a photon that is detected, right? And then you can try to make predictions about the internal state of the system. In this case, is some complicated nonlinear optical system. And in this case, it's a little bit different. It's more condensed matter-ish. So this is a quantum dot where you can monitor injections or extractions of electrons into the quantum dot. So there's a little dot here. And this is a little lead, a wire, and an electron can tunnel from into the dot or out of the dot. And they monitor this continuously by applying what's called a quantum point contact that measures this kind of current here. And these are the quantum jumps happening, right? So every time the current jumps up, it means that an electron left. Every time the current jumps down, an electron came in. So you can really monitor the jumps that are going on. Okay, so essentially the dynamics of a master equation has the quantum jump dynamics has two things associated to it, right? One is the random times where these jumps occur, and the other one are the random channels that might click, right? So the channels are the individual jump operators. So I personally like a lot, to think about the game Guitar Hero, for example, or any other kind of video game, where essentially you have these buttons that you're pressing. These are the symbols, right? And they also occur at random times. So your quantum trajectory is now a pair of symbol and duration, symbol, duration, symbol, duration. These are the symbols that are emitted at the random times that they are emitted. You can easily define instruments for one jump. So this is the instrument that tells you that the system evolved for a certain time tau without a jump, and then it jumped. So L0 is no jump operator, JX is the jump operator. So you can kind of easily just write down the instrument that describes each pair of these data points. You can also do, suppose you don't care about the times, right? So you wanna look at a sequence of symbols that was emitted here, but you don't care how, the time between them. So you can just marginalize over times and obtain a set of instruments that it just concerns the symbols without the time tags. I'm not gonna talk about this much, but we've been doing a lot of work. So these are just some of the references that I want to flash here into doing essentially metrology of these kinds of stochastic processes. So how do you do parameter estimation, classical Fisher information, and all that kind of stuff. So essentially the idea would be that you have a machine that is producing these symbols. This is your kind of hidden Markov model, for example. And this machine depends on some parameter data, and you want to essentially estimate this parameter. And so then it matters what kind of data do you use. So if you use all of the data, all of the symbols, you're going to get a certain Fisher information. But if you only use part of your data, you get less. So essentially a data compression. So the Fisher information for the entire data set scales proportionally to the data set for any kind of process where the correlations are not insane, right? So usually this quantity here is called the conditional Fisher information and describes essentially the information rate. Every time you see a new symbol, how much information do you gain about your parameter? And I think this is a really cool object because it's telling you how much you can learn on the fly, right, as a rate about something that you're trying to estimate. But this would, in principle, require the full data set. So what you can do is you can do silly kinds of data compression. For example, you might just want to count the symbols. Suppose you just want to count, here's a bit string of zeros and ones, and you just want to count how many times I observe 0, how many times I observe 1. So this is has less information, right? Or you could count pairs. You could say, how many times I observe 0, 0, 0, 1, 1, 0, and so on. This has a bit more, and so on. So you can build these kinds of I would call them empirical distributions and essentially characterize the metrology about them. But now I wanted to focus a little bit more time on this recent paper that we put out with my PhD student Abe and also Patrick Potts over in Basel, which tries to apply these ideas to thermodynamics. So here is an example of a double quantum dot, where essentially I'm going to pretend that the system can only hold 0 or 1 electron. So I have a 3-level system. The levels are no electrons, electron on the left, electron on the right, just a 3-level system. And I'm going to assume that this system is connected to 2 baths. There's a hot bath and a cold bath, right? And so essentially I have 4 kinds of jumps. I have what we labeled here, injection hot, extraction hot, injection cold, extraction cold. These are the observable jumps. These are the symbols, right? Every time you see an electron tunneling in, an electron tunneling out, that's what you would observe. And now what we started thinking about is, can we identify some thermodynamic cycles from this kind of process? So suppose we only get strings, right? You only get these emitted symbols, and we just look at these strings long enough, and you say, okay, what can I see? Like, what do you see from such a string like this? Can you identify something, right? So our motivation is the following. A process where essentially, energy flows from the hot to the cold bath. So something like tack, tack, tack. This is associated to essentially extraction of chemical work or extraction of work in general, right? Because you're making heat flow from hot to cold. Whereas a process that goes in the kind of uphill direction is a refrigeration kind of process. It means you must consume some kind of work to make heat flow from cold to hot, right? So motivated by this, can we, just by looking at the strings and nothing else, can we identify thermodynamic cycles? So first of all, in addition to these two, there's of course these possibilities. So these are the not so fun ideas, right? This is essentially an electron comes in here and then leaves. Or same with the cold bath. So these are processes that are idle, nothing really happens, right? But in addition, there's also another problem with this, which I think is described by this kind of substring. So suppose you observe this, exactly this combination. So an injection comes in from the cold bath, an injection comes in from the hot bath, and then you observe an extraction to the hot bath and an extraction to the cold bath, right? What happened here? So it's actually ambiguous, because excitations are indistinguishable. So it could have happened that you had essentially two cycles kind of interweaved. So something like which is cooling, a cycle that goes this way and a cycle that goes this way, and they're kind of mixed together. Or it could have that you just had 2 of these bounces, like tum tum and tum tum, and you don't know, right? So you don't really know, you can't really distinguish an individual cycle just by looking at the strings.
Sorry, didn't you say you can have only 1 electron?
Sorry, yes, I contradicted myself. I will conclude from this that we can actually only have 1 electron. In principle, you're right, sorry. In principle, you can have 2 electrons, and then this makes sense. If you can only have 1 electron, that's where I want to get you. Okay. You precisely avoid this kind of problem. Sorry about this. Thank you for pointing that out, yeah. So in principle, if you can have 2 electrons, this kind of thing could happen. If you can only have 1 electron, this cannot happen. And that's exactly the point that I want to make.
Excuse me.
Yeah.
If you go, here you're not putting time tags to those measurements. Are you going to address that later? Because the first thing that I think is that you take a Fourier transform of that thing and you find the peak at the separation between even and odd combination of left and right, or that doesn't happen. So
we didn't really throw away time tags in the sense that to each of these symbols, there is an associated time tag. And this will tell us information about how quickly a cycle runs, right. Which is, so that is still implicit here. I don't know exactly about like taking just the Fourier.
Because there is a characteristic, I mean, they would have different energies, right? The left plus right or left minus right, the electrons.
Right.
So that should give a beating for the electron jumping left and right with a characteristic time.
I'm not sure I understand. Maybe we can discuss.
Right, okay.
Because to be honest, I mean, it might be that I mean, I don't know. We've been just trying to think about this question of just by looking at these strings, even with time tags, can you identify stuff? And if you're saying that, somehow again, that would be fantastic. We'd be very happy. Our conclusion was that if, again, the system could have, in general, 2 electrons here, for example, this wouldn't be possible. Yeah.
So one would think that, for example, an IH first and an EH directly after, you could basically just throw out, but because it doesn't do anything. But this is not necessarily true the other way around, because if you first eject and then inject, you lose coherence. So is that something which is important in your system or not?
That is a great point. Yeah. So we do expect that, if you observe something like this and this one kind of quickly, you would expect that it's more likely that this was just a bounce, right? But of course, it doesn't have to be, because everything is kind of statistical. So it could have been that it was not a bounce, it was actually the other cycle, the other way around. So I guess what you're...
So the question is where, for which orders do you actually kind of keep in, do you keep making a difference? So which parts of, are you only caring about where your electron sits, or are you also caring about the coherence of your electron? Because in the one case, the history matters, and in the other, I guess it doesn't. Right?
So with this kind of formalism, we can take into account what is the coherence of the electron given a certain sequence of observations. So that we can account. And of course, if the electron leaves, then of course, the whole thing resets. So there are special points where the whole thing resets. But we can. So we can actually take into account.
So, but it should be relatively easy then to find the places where you say, okay, here's a reset. We can basically cut that part of the string off and forget about it.
So, but if I understand correctly, what you're saying is more like, can we make a guess about which of these 2 happened based on information? And that we can, but it's always a guess, a probabilistic guess. It's never like...
But it's also the question, do you try to actually shorten your strings to simplify your problem by saying, okay, there are certain string sequences where we can just say, forget about it, that doesn't do anything.
Right. So we haven't done that. We actually just restricted to the one. Having one electron is very common for experiments. It's called the Coulomb blockade regime, and they have it all the time. So actually, for them, it's pretty natural. So far, we've mostly restricted to that. But I think that's actually a very good point. Essentially, doing a kind of a Bayesian guess, and then just kind of throwing away the ones that you're not super sure about. That is very good. Yeah.
Clarifying. Are you looking for patterns in this string?
Yes. Or patterns which in particular have thermodynamic meaning.
And like when we say patterns, you mean like repeating patterns? Like, do we expect like repeating patterns because it's a thermodynamic cycle?
So for example, I guess these would be just the 4 patterns that we would be looking for. This would be the kind of the simplest, the fundamental pattern, so to say. So essentially a sequence which is IH-EC, IC-EH, IH-EH, EC, IC-EC. And these would be kind of just the patterns. In the simplest case, we would just be looking for repetitions of this. You're right, in a more complicated problem, then you could be looking at repetitions of longer strings, right? Or patterns, which is, 3 injections, 1 extraction, blah, blah, blah. Yeah. I
was wondering like what actually guarantees that there will be repeating patterns in the string.
Right.
What is like the physical intuition that there should be repeating patterns?
When you say repeating, you mean the pattern repeats or that it repeats periodically in time?
Yeah, periodically in time, certain like a Foucault type of.
Right. So absolutely none. In general, there will be no.
Random.
Yeah. But there are some sequences that can have that. So there are sequences that and this happens more in like classical hidden Markov models where they see that after 20 symbols, all of a sudden the whole thing repeats. And they can identify. Yeah. So that does happen when they're trying to identify more general patterns. For the problems we consider, that doesn't really happen. Okay, so the first thing we then set out to do is say, okay, so let's say that there's only a single excitation going on because we want to avoid that kind of problem. So what we realize is that a single excitation, it places certain restrictions on the kinds of models that you can have. And in particular, it says that your entire Hilbert space has to be block diagonal. So your Hilbert space has to have two corners. There is the what we call the post-injection corner and the post-extraction corner, in the sense that every time an excitation comes in, the system has to go to one corner, and then when an excitation is extracted, it has to go to a different corner. There can still be, in a more complicated model, there could still be plenty of dynamics going on within these subspaces, such as work extraction and so on. But the effects of the heat paths have to be such that you have this kind of block structure. And what is cool about this is that now we convert a sequence of jumps into a sequence of cycles. So we identify these 4 cycles. We're not very creative with the name, so we just call them cycles 1, 2, 3, and 4. But this is like an engine. This is cooling. This is idle hot and idle cold. And sorry, the letters here are wrong. This should be like hot instead of left and cold instead of right. But these are the same cycles that I was showing before. Right? And so now, when you have just a single excitation, all of your jumps are always injection, extraction, injection, extraction. And so we can just bundle them, each pair IE, into a cycle, right? And instead of looking at bit strings of jumps, we can just think about bit strings of cycles. And we can define instruments for a cycle. We can just say, you know, this is the instrument for a cycle that is of type X, where X is 1, 2, 3, 4, and has a duration tau. So this is, you know, how long does a cycle last? And we can now answer a bunch of questions. For example, you know, what's the waiting time distribution of a cycle? How long does a cycle take, right? Which cycles are more likely to happen, right? We can also talk about cycle correlation, kind of like cycle bunching and cycle anti-bunching. Suppose you observe some kind of heating. Does it mean that the next cycle is going to be cooling, or does it make it more likely that the next cycle is going to be cooling, and so on? Can we have cycle correlations and so on? And also some questions about intermittency. You know, these 2 cycles here, they're not very fun, right? This is just bounces back, bounces back. So how many of these useless cycles happen between useful cycles, right? So we can talk about intermittency. You have a machine, but it's not operating regularly. It's operating in a very kind of erratic manner. And sometimes you have useful cycle, but you can have many, many useless cycles in between. Okay, I mean, this is just a few of the definitions, but let me show you an example. So this is a 3-level maser, which is essentially the same as the double quantum dot. So it's a system of 3 levels, 0, 1, and 2. You have the levels 0 and 2 coupled to the hot bath, levels 1 and 2 coupled to a cold bath, and this is coupled to some kind of coherent interaction, for example, a cavity, right? So a radiation in a cavity. And then for this kind of model, again, I can apologize that it's cut here, but the cycles are just a heating cycle. An engine cycle is something that goes like clockwise, a cooling cycle goes anti-clockwise, and then you have the 2 idle cycles here. And so we can ask questions such as, which cycle is more likely to happen? So that's what's shown here. So this is the engine operating on average as a refrigerator and on average as an engine. And we see that when it's operating as a refrigerator, it is always more likely to either observe a cooling cycle, which makes sense, or an idle bounce. This cold bounce, right? And in fact, the bounces are always more likely to happen, right? So the useless cycles, the idle cycles, they are always more likely to happen. But of course, the second most likely is just a cooling cycle. And then we can also talk about waiting time distributions of each individual cycles, about average time a cycle takes, and so on. And finally, about intermittency of cycles. So I'm not going to go through a lot of detail, but this is, you know, how many useless cycles between useful cycles. And this is how long does it take between 2 useful cycles, right? So these are, of course, related questions, but they're different. Because sometimes you can have cycles that are useless, but they're very quick. And so you can have many of them, but they actually don't take up a lot of time. Okay. And now I just want to finish up by mentioning more recent work that we're doing with absorption refrigeration. So this was actually motivated by this paper, which implements this absorption refrigerator in a superconducting circuit system. So let me just quickly explain this. So an absorption refrigerator works very much like a sideband laser cooling. It's very, very similar. Except that instead of lasers, you have heat baths. That's pretty much the difference. And the way it works is somewhat like this. So you want to pump some energy from a cold bath, right? So you want to pump energy this way, essentially from a cold bath to a hot bath. And the way you do it is through a kind of a three-body interaction that only matches in resonance whenever this excitation couples with another one, which comes from this, what we call the work bath. And so if this energy plus this energy matches this energy, then there's a resonant tunneling, and essentially you can pump energy this way, right? So the nice thing about an absorption refrigerator is that in principle, it is fully autonomous, right? You can just have 3 heat baths, you can just leave them there, and they're gonna pump energy away from the cold bath through this kind of resonant process. And this is a little bit the mess that you would get if you look about the transitions, right? Sorry that it's a little bit faded here, but this is a kind of semi-classical description, right? So we have the possible configurations of 3 qubits. So we can imagine this is 1 qubit, another qubit, another qubit. And so, for example, you can start in a state that has no excitations. Then you can absorb an excitation from the cold bath. So this transition from here to here would be going from here to here. Then you can absorb an excitation from the work bath, so go this way. Then you tunnel resonantly. So you see this frequency is resonant to this one. So you tunnel and essentially transfer your excitation here and eventually dump it out. So a cycle that goes this way would be a cooling cycle, right? So you can imagine that your system is undergoing this complicated dynamics in Hilbert space, and you would try to then observe these kinds of patterns. And that's the kind of thing that we're working on right now. This is clearly a problem that has many excitations, and that's so it doesn't fall into the category that I was describing before, because you can actually have 3 excitations here. So we're still kind of developing the framework to describe this kind of process. But the idea would be to think about this as some kind of cooling on demand. So imagine that you want to have a machine that's ready to cool whenever an excitation comes in here. Right, so you want to keep this as cold as possible. So if an excitation comes here, you want to pump it away as quickly as possible, right? And so you have to then ask, how ready is the machine going to be? And if it's ready, and if an excitation comes, how successful is it that the cooling is actually going to happen? Because it could be, it's stochastic, so all kinds of weird stuff could happen, all kind of weird things could happen. It could be that an excitation comes in here, there is another excitation here, and you're ready to go. You're ready to kind of convert yellow and blue into red. However, since it's stochastic, it might be that this excitation just goes back to the bath, and then you're screwed. Or it could be that when you're finally ready to go, an excitation comes in from the hot bath where it shouldn't be, and just takes up the place where this new excitation was going to be pumped. And so again, you're screwed. So these are some of the questions that we're asking about how often do you actually get a successful cooling. Yeah.
Sorry, I'm a little bit confused especially from your level scheme on the right side.
Mm-hmm.
That seems to be completely symmetric. Why does that come in the refrigeration direction?
Why does the
Why? I mean, it seems to be equally likely to go from hot to cold as from cold to hot.
That's a good point. So actually, what breaks the symmetry is the temperature, which makes the arrow going this way or this way.
I see. Okay, that was right.
So for example, because it's thermal, and you have to. The game here is that.
So basically, your injection on either the hot side or the cold side is higher than the other.
Yeah, and this doesn't work for all temperatures. So there's like temperature regimes where things work. Essentially, this has to be colder than the hot bath, and the hot bath has to actually be colder than the work bath. So the work bath has to be the hottest of all of them for things to work. Yeah. Okay, so that's pretty much all I wanted to say. So I focused on this idea that when you do sequential quantum measurements, you get a time series, and I personally find this quite fascinating. I like it very much. The idea that you get a very correlated stochastic process whose underlying correlation properties reflect this kind of underlying quantum system. And I tried to discuss a little bit about how to essentially do Bayesian inference and metrology of this, and also how to do a little bit of thermodynamics. And so that's all I had to say. Thank you for your time.
Thank you.
It's time for a couple of more questions. Maybe Johannes, you go first.
So thanks a lot for very nice ideas. I have a very naive question, basically out of ignorance, kind of. What information do you get from kind of doing this type of analysis compared to just calculating the steady state of the whole Hilbert equation and then calculating heat currents or something like that?
Yeah, that's a great question. So if you look at the steady state and you look at the average current, right, that's fine. And of course, that's kind of our day-to-day business. But you can also look at current fluctuations, right? This is directly related to the current fluctuations, and they can actually be quite significant. So the steady state current is just an average current, but in reality, there's a lot of fluctuations. And so this is actually precisely, the motivation was exactly to understand the current fluctuations in a more kind of time-resolved or more detailed manner.
Thank you. So, I mean, I guess going back to the previous question, I mean, from the Limbladian, you can also find correlation functions, right?
Sure,
that will
yeah.
tell you about these fluctuations, right? So, like, it's somehow all connected, right? Yeah, so that's a comment. My question actually is, so this seems to work very well when you have this restriction to a single excitation. But on the other hand, if I think about thermodynamic systems or even mesoscopic systems, you have many particles, right? So how you mentioned this slightly, but how are you thinking about like scaling this up such that you let go of these restrictions? Does this formalism is it not useful anymore, or is it just things become manageable? Can you comment on this?
Yeah, no, absolutely. So just very quickly, I kind of skipped through this, but this is one formula that connects with steady state. This is the steady state current. These are the probabilities of two types of cycles. This is the cycle time. This is a general relation that we found, but this is only for the averages, not for two-time correlation functions. You're absolutely right. Yeah, of course, from master equation, you can just do quantum regression or whatever and get some kind of two-point correlation functions. But that still doesn't explain. I mean, it's exactly the same as if you talk about, say, the G2 function in optics, right? Where the G2 function is a correlation function, that's fine. But what's really underlying is that G2 function are individual clicks, right? So that's kind of what we're trying to think about, just looking at it from kind of a more time-resolved or individual click perspective. We still haven't found similarly nice relations for, say, connections with two-time correlation function. We're actually working on that right now. That's our kind of goal, to essentially relate current fluctuations or two-time correlation functions in general with this kind of picture, right? And that's essentially work in progress. Your second question?
And it was more like, what about mesoscopic systems?
Yes. Right. So this single excitation is indeed a little bit restrictive. One of the things that we're working on right now is essentially thinking about these processes in terms of what we call excursions. So the special thing about this is that, we don't really know what's going on in Hilbert space very often, but we know that there are a few events which completely reset your memory. So for example, if you observe in this example 3 emissions, then you know for certain that you're here, right? And so you have this kind of truncation of the memory, and you can think about it in terms of excursions. You can say, well, I'm going to describe my thermodynamics within each excursion. So within each of these kind of reference points. And in that sense, you're not restricted to a single excitation anymore. It still doesn't scale up in the sense of many excitations, like many bodies. So that in that case, no. But I guess in the many body case, you don't really want to look at this kind of thing. You just want to look at like steady state currents or two-point correlation functions, right? So because maybe I can kind of come back here. This is like typical kind of 3-level maser coupled to a cavity. The individual jumps of this thing make sense if you have a single 3-level atom, right? But if you have 10 to the 23 of them, or even 1,000 of them, the individual jumps matter less, and kind of average currents and so on matter more. Yeah, so my short answer is that we have no idea how to extend this to anybody. Yeah.
If I can go back to my original question, this is actually what I was interested in. So there you have something that tells you the characteristic time of each cycle, and there is a characteristic time.
Absolutely, yeah.
I mean, my naive interpretation would be that these quantum dots are coupled, and the coupling, if they are not coupled, I mean, it is like there is a wall. They are coupled so that the energy level are split.
Yeah.
Right, in a symmetric and antisymmetric one.
Absolutely.
So that is the corresponding to that timing. The 1 over delta E is that peak. Is that the case?
You mean to this peak here?
Right.
No.
I mean, what is isn't that gives you I mean, you feed an electron to the left,
Yeah.
this blobs to the other side and then goes to the right. So the time of blobbing must be there, right, for the cycle, for the
Yeah,
deterministic
but
time.
I think it might be a slightly kind of more complicated combination of this kind of level splitting and also essentially the coupling strengths and temperatures. Because, for example, this also describes the idle cycles, like something that, just like a bounce in this direction, right? Which would still be happening even if there was no kind of, even if there was a wall, this would still have a distribution, right?
I see. So that would be even if the transfer from left to right would be ultra fast because it's dictated by the tunnel from.
Yeah.
I see.
Yeah. So I think it's a.
And then the fact that they coincide is that this injection and extraction is the dominating thing. But what if it were much slower, the coupling? Then would you see these things split?
To be honest, I don't have a good intuition. I mean, what I can tell you is, I mean, we could just kind of plot it here, and all I remember is that there is kind of a non-trivial coupling between, you have two coupling strands, so two baths, and also this kind of coherence. So this is essentially 3 timescales, and they do conspire a little bit in non-trivial ways. But I don't have a lot of intuition of how the distribution itself would change. The only thing that we do have an intuition is that, if the kind of coherent tunneling is big, you get these little wiggles. If it's small, you don't get wiggles, right? It's just kind of very normal, these interference effects in waiting time distributions.
Thanks.
So because of time, I mean, lunch beckons, but it's also a very good time to be discussing things, right? I mean, this is the entire purpose. So without further ado, join me in thanking
Thank you very
Gabriel.
much.
Lunch is